now let us see a bit inside the testing transformer. So inside any transformer you have primary as well as secondary winding, right? So the main difference when it comes to winding, okay, let us discuss about winding of this transformer. So in a power transformer, we usually avoid the capacitance part. In a power transformer, we usually avoid the capacitance. Capacitance means it can be like what? Inter-turn capacitor. Between every turn, you are placing some insulation, and because when you have insulation and you have your conductor, then it's a capacitance. So you can have inter-turn capacitance, or between the LV and SV windings, you can have capacitance. So these capacitances we are not considering when it comes to a power transformer. In a power transformer, this capacitance is what? It is neglected. Right, it is neglected. Why it is neglected? Frankly, it is due to the reason that we usually neglect the capacitance of a transformer. Right, you might have seen when you are considering a transformer equivalent circuit, we usually neglect the inter-turn capacitance and all. Right. So why we are neglecting this capacitance? Because one reason is that it is very low. The capacitance value is what? It is comparatively very low for the winding. Another reason is that we are operating our transformers at what frequency? At our power frequency. Means what? At 50 hertz, right? When we are operating something at 50 hertz, then your capacitance value or the reactance value, what is XC? X is given by 1 by omega C. Right, Xc is given by 1 by omega C. Since your power frequency is comparatively lesser, due to that what? Your capacitive current, capacitance, reactance will be higher. So that your current also will be what? Current will be lesser. Right, whenever your reactance or resistance is what? Decreasing, then you have more current. So due to these reasons, we are not considering the capacitance as such in our power transformer equivalent circuit. But when it comes to a testing transformer, what is our problem? When it comes to a testing transformer, like I am having a testing transformer here, and in that what will happen? We are not dealing with our power frequency or what? 50 hertz, right? So as I told already in a testing transformer, what will happen? We are switching it, and whenever whenever we have some insulation and we are applying high voltage, what will happen? At a particular time it is conducting. So the behavior will be like what behavior will involve lot of transient behavior, right? And means it is prone to switching all through its working, and lot of transient behavior will come. When we say that there is something transient, it means what? It means that we are talking about high frequency. Right, the switching operation, the preliminary part of switching operation, we call it as what? Transient phenomenon, and it means what? It means that we are talking about high frequency. Right, normal operation it might be power frequency, but when such a breakdown or such thing occur, or when we are switching under all those conditions, your testing transformer is undergoing this transient behavior. So while considering the testing transformer, we have to consider the capacitance. Why? That I will tell you now. Means anyhow, one thing is clear that what we are dealing with high frequency. So what is our capacitive reactance? Capacitive reactance is given by what? 1 by omega C or 1 by 2 by Fc. Right. So capacitive, when your frequency is increasing, the denominator will increase. So that what will happen to capacitive reactance? Capacitive reactance will decrease, right? So when your capacitive reactance is decreasing, so the current through that thing, the current through capacitor, right? Capacitive reactance is increasing, so the current through capacitor, it will increase, and because of that it will become considerable. Means it will become the considerable part of total current. So that is why what we have to consider the capacitance part in our testing transformer. Understood? In a power transformer, since the capacitance value is low and we are operating it at power frequency, we don't have to consider capacitance. But when we are taking a testing transformer, then we are not operating at power frequency. Instead, we have to deal with lot of transient behavior. Which transient behavior means what? We are dealing with high frequency. Whenever your frequency is higher, your capacitive reactance is lower. When capacitive reactance is lower, because of that what will happen? The current through the capacitance will increase. That is why it will become the considerable part of the total current. That is why we have to consider capacitance. Okay. Now let us see the winding diagram. Okay. Or how can we represent this winding? Okay. let us take one winding, okay, like you have the high voltage winding, let me say, and let us take the winding in portions like this, okay, like each winding, let me say, or just it's a what I can say, it is just a representation, okay, just let me take it more clearly. Okay, so this is the total winding, let me say. One part of the winding, let us say we are, with respect to ground we are considering, so I am grounding this one terminal. So, two types of capacitances we are considering. One is between each winding. Between each winding means what? It will come parallel like this. So, this is the one type of capacitance that we are considering. Between each winding, it will come like this. All through the winding you will have, between each winding you will have some capacitance, that is called what? The inter-turn capacitance, right? This is the inter-turn capacitance like this, okay. So let me say this is CS1, means the first coil, this is second, this is third, like this will be what? CSN minus 1 and this will be CSN when you have n number of turns, okay. And this is how we represent. Another kind of capacitance that we are dealing with, it will be this way, like what? Like we have with respect to, let me say, this is this way, and like this is like with respect to ground, let me say. So this is what, with respect to C, this is called as CG, with respect to what? LV and SP winding. Okay, we are considering only the half portion of the winding, so this is how we represent it. This is CG, okay, with respect to ground, the winding between the capacitance between LV and SP windings. So this is like this, okay. This CG values will be marked as constant and CS is differing, okay. We will see the explanation later. But one main part is that this is where you are applying your potential. This is where you are applying your potential, right? You are applying your potential here, and this is your ground. So that is the two parts here. You have applied your potential like 100 kV here, and this is your ground. And throughout this section, between this capacitance and inductance section, your potential is getting distributed. Your potential is getting distributed. Now, interesting thing that you can identify here is that here your current is like what? Current is distributing, right? Current is dividing at this point. But since your potential here is more, the current passing through capacitor CS1 will be comparatively more, because again what, this one have to supply all the other currents. So compared to CS2, CS1, your potential drop will be higher, because since your current also is what? Higher. Potential drop will be higher and current also will be higher. When it comes to the last portion CSN, which is nearby ground, here what? Here your potential drop will be lesser and your current also will be lesser. Understood? So the main part is that it is not when you have a equal resistance like this, equal resistances are fed like this, let me say, then what will happen? Your all the potential drop across each resistor will be same. But you have a complex circuit here, and here your potential drop is not going to be same all through the different lengths of all through the winding. Understood? From the live wire to here. Okay, so we can say that your potential distribution is what? It is non-linear. That is the important point. Okay, your potential distribution is non-linear all throughout the what I can say, all throughout the winding. Okay. So once again I am saying CS means the interturn winding, CG is the capacitance between what? LV and SV winding. We are taking only considering what? One winding at a time. This is the each winding inductance. Understood? This is the each winding inductance. So what now, as I already said, and when it comes to high frequency, then your inductive reactance will become what? XL equal to 2 pi FL. So your inductive reactance will become higher, and that time, let us say we are only considering what? Capacitance alone. So we can consider what? Capacitance alone. If we consider,
hello. Okay.
So with capacitance alone we will consider. Why? Because our inductive reactance is comparatively large, so we can avoid that. So if we consider only the capacitance alone, what it will become? Our inductance, all our inductance will go, right? So what it will be? It will be just capacitances, right? CS1 like this up to the parallel capacitance branches. This is CSN, this is CSN minus 1, this is CS2, this is CS1. This is our live terminal. And along with that, what you will have? You have this CG also, right? You have this CG also like this, right? So this is the ground part. Okay. So this is the CG. Like this, you have your equivalent circuit. Again, here also what will happen? Here also, since there is a division of current and these capacitances are not equal, because of that, you have your potential distribution to be non-linear. What I am meaning, you are going to understand. Okay. Let me say this in this graph, this is the potential. Okay, this is the potential, and let me say this is 100 kV or whatever be the live wire and whatever potential you are giving. And let me say this is what? This is the winding length. Okay, winding length up to what? Up to means at this point you are reaching your ground part. Understood? At this point you are reaching your ground. So when I say it is non-linear, or instead of this capacitances, if I had just resistances, equal resistances connected like this, then my potential distribution will be which way? It will be a straight line like this. My potential distribution will be a straight line when I have all the resistances of and each of them are equal. But in the situation here, when we take the testing transformer winding, then it will not be what? It will not be a straight line like this, or we will not have a linear distribution. Instead, what we will have? We will have a non-linear distribution. Okay, or let me say, we will have a non-linear distribution like this. Understood? So from the first turn you have more, let me say you have more potential drop, but whenever it is coming to the nth turn, or when we come up to here, then what? With respect to winding length, there is not much potential drop. Understood? Or what happens is that most of the potential drop, or most of the stress, voltage stress, will happen on what? Will happen on the nearby this side, and lesser voltage stress will happen on what? The ground side. Understood? So that is what is meant by non-linear distribution. Sorry, non-linear distribution of potential. Non-linear distribution of potential. That's the problem. So we have to encounter that. Understood? Why? Because when nearby ground, it is having lesser voltage across it, so that it will have lesser voltage stress. You can provide lesser insulation, let me say. But when you come to nearby this end, the live wire, then what? Your voltage stress is more. So that's the problem. Okay. What is deciding is like this. Let us say your CG is 0. Let us say your CG is 0. Then what will happen? Then this current division is not there. Understood? Current division is not there. So what? It will be a complete set of capacitances, or series capacitances alone. So because of that, what will happen? You will have a linear distribution like this. When your the CG is completely gone, then you will have linear distribution. But that is that is like the ideal condition, and that is not going to happen. So we define a factor alpha, which defines what? The distribution, or the potential distribution alpha is given depend on this alpha. Alpha is given by root of Cg divided by Cs. Cg is what? Cg is the LV to HP capacitance, and CS is what? CS is the capacitance. Alpha is defined as root of Cg by Cs. Cg is the LV to HP capacitance, and Cs is the inductance capacitance. Okay. Whenever, let me say, alpha is 0. Alpha is 0 means what? Cg is 0. Under that condition, what you will have? You will have your potential distribution to be linear. This is the potential, and this is what? This is the winding length. Okay. So it will be linear. But when, let me say, alpha is 5, then what will happen? Then you will have a distribution like this. Alpha is 10 means it will be more non-uniform, means more of the potential drop will be along this side. So this value alpha will determine how much your potential distribution is going to be. So it's an important factor in design. Understood? It's an important factor in design. Why? Because when I say potential distribution is non-uniform, it means that towards the live winding part, what will happen? You have more voltage stress. Understood? The voltage stress is more here, and here it is lesser. Understood? So that is a problem in design, and now we will see how we can overcome that situation.